Hi everyone, I'm Bella Nasirudin. I'm here to talk about my work, which is on. So the Haslam 408 megahertz map is a comprehensive all-sky map of the galactic diffuse emission. It comprises data from 4 separate radio telescopes, the two Jordan Banks 76 meters in the UK, the Effelsberg 100-meter telescope, and also the Park 64-meter telescope. So it is widely used as a synchrotron template for foreground removal. This is done by coupling the data with data at other frequencies using a power law relation. However, there are several issues with the Haslam map. First, there are artifacts in the map from imperfectly subtracted extragalactic sources. Then there are large-scale stripes caused by drift scan noise. These two have been addressed in a previous work in 2015. But there's also uncorrected gain factors. It is usually quoted as around 10% level. But studies have shown that by Monsaf 2021 and Walensky 2024 that their values could be higher. So currently, methods on gain or scale corrections or calibration involve more model selection, which is done by Pagano and Walensky. There's also nested sampling and Bayesian model comparison, which is what's done by Carter. And other than that, there's also comparison to radio observation at a low frequency. That's done by Monsaf using the IISc data. So what we're trying to do is we use the Bayesian statistical method to constrain the gain factor and true sky signal at 408 megahertz by combining low frequency radio experiment data with Gibbs sampling. So we sample the posterior for the gains and the true sky signal. And we also include a Gaussian constraint realization technique, which I will explain in a bit. So this is our data model and posterior. First, we assume that the signal at lower frequency follows the power law with a known spectral index. We can then model the Haslam and the X experiment data according to these equations. So here S is the signal, Y here is just the operator matrix, G is the gain, and N is the noise. Now for the X experiment, we assume that it's a global, something that is like a global experiment. So it has a beam, a wide beam here, and it's convolved with the signal at low frequency, and it has noise as well. So combining them together, we get this equation. So following Bayes' theorem, the posterior distribution for parameters G, gains, and S, the signal, are then given by this curves. The posterior should be proportional to the likelihood multiplied by the prior. So big G here is the covariance of the gain, and big S is the covariance for the signal. Now, I'll just do this very quickly, but we also assume that, assuming Gaussianity, so they follow the Gaussian distribution, we then use the maximum a posteriori method. We take the derivative of the equation and set them as equal to 0. Can then rearrange the terms and what we get as this solution. So G hat and S hat here are the estimated and the estimated gains and the estimated signal. That is the basically Wiener filter solution. And the terms in the bracket here is the variance. So we finally add Gaussian constraint realization technique by adding the omega terms. So the omega terms are just random numbers with mu of 0 and sigma of 1. They are then scaled according to the variance of this solution. So, and these are our final equation for Gibbs sampling. So I'm gonna explain what we use for the simulations of the sky. So we use PyGDSM to generate the synchrotron radiation map at 408 megahertz. we then degrade the map to n side of 128 using HillPy. And we generate the gain following a normal distribution with mu of 1 and sigma of 0.05. So here we assume that each zone has its own unique gain, but is subdivided into 10 zones, 10 subzones. So here are the zones that I've talked about. So there are only 4 instruments, but we have decided to let the intersection between the zones to have their own gains, basically. Now, we then use a power law relation to generate the data at lower frequency. So this is between 50 to 150 megahertz. And then we use HillPy to convolve the X map with the Gaussian beam. This is the preliminary results for the gain factors. Now, for our standard case, we assume a noise level of 100 and 800 millikelvin for X experiment and Haslam respectively. So clockwise from top left, we have the true gain, and this is the estimated gain. This is the standard deviation between their difference, and this is the fractional difference. Notice that down here, when you're along the galactic plane, you get the lowest difference, basically. And as you can see here, it's a bit skewed, it's a bit biased. It's like positively biased by a little bit. So the range here is from minus 0.15 to 0.4% of fractional difference. So the gains are slightly biased. Now we look at the same plots for the true signal. So clockwise from the top left, we have the true signal. And this is the estimated sky. This is the standard deviation of the difference. And this is the fractional difference. Notice that this look more noise-like. And the lowest difference is the same as the true gain, where it's along the galactic plane. But for the standard deviation, the highest difference is actually along the north spur. Which is also where the Effelsberg zone is. Now, we also do the same thing, but with a few different parameters. So what I've shown you before is the blue one, or what we call standard. Then we have the lower noise for X experiment, which is 50 millikelvin. Then we have lower noise for Haslam, which is 500 millikelvin in green. We also have confused noise for Haslam, for red, where we assume the Haslam noise is 800 millikelvin, but the true noise is actually 1,300 millikelvin. And we also have a larger beam for the X experiment. So I'm showing you the histogram of all this. So here from top left, we have the ratio. So S over, estimated signal over S. And this is the difference between them for upper right. And then lower right, we have the difference between G hat and G. And then we have the ratio between the estimated G and G. So as you can see here, you get a tighter constraint when you have lower noise for Haslam. But other than that, the other cases seem to give the similar constraint for S, for the signal. But for the signal, they look more, the distribution follows a normal distribution. But if you look at the gains, they're, for all cases, they're all slightly positively biased by around 0.4%. And the constraints are also similar. So there is no advantage to having lower noise for Haslam if you want to figure out the gains. So we've also tried to have more subzones. So instead of just having 10, we increase it to 100. So I'm showing you the same plots. Here, the more zones is in magenta. So for the signal, you get similar distribution as well. As for the gains down here, although the estimated signal looks a bit more the distribution looks a bit more normal, their mean is actually similar. Here I've plotted the mean for the Morzone versus standard, and they line up almost perfectly here. So there is no difference if you increase Morzones. Well, so this is my conclusion. We presented a Bayesian statistical method that combines gate sampling and Gaussian constraint realization technique to constrain the gain factors and true sky signal using data from low frequency radio experiments. They show that the results for the gain constraint is slightly biased by around 0.5%. And next, we will constrain the spectral index for the power law relation. What we've done now is just with one spectral index, assuming everything is the same. But next, we will try it with different spectral index and see what we get. That's all for now. Thank you.